My topic of the presentation will be giving you a framework on what is under development, both at European level, but also under collaboration. So what Italy is contributing to the, let's say, hyperspectral community, how it's contributing to the development of the hyperspectral sensor, both at national and European level, and how much the link are related also to, you know, the worldwide community. So also collaboration with NASA, JPL, and other type of collaboration. I hope this can, you know, give you a flavor on what is under development and what are, you know, the basic interest that the hyperspectral community can get out of this huge research investment and also industrial investment. So Copernicus is a regulation at European level, so it's a law. We have to keep in mind that because under this European law, the European Union and all the member states are developing what we have called, you know, the upstream development. So a lot of satellite already operational, but also new evolution. And the hyperspectral one, the CHIME, Hyperspectral Imaging Mission, CHIME, is one of the new development. But we have to keep in mind one basic point, that Copernicus is something that has been developed in the last 20 years as a starting point for research, then for operational, so building up operational services. And now we are in the third phase where the European Commission has started to put into different regulation, and I'm citing the one 746 of the 2018, where the European Commission has finally included the use of Copernicus Sentinel satellites that must be integrated with EGNOS Galileo in order to have an official tool for controlling and granting the Common Agricultural Policy payments. This is a key issue because it's important to understand and it's important to consider that Copernicus has three main important points. First is open, free, and free of charge. So all the data and information, both you know, deriving from Sentinels, from satellite, but also, you know, from in situ data and also modeling, so from the core services, can be downloaded for free from everybody. The other point, important point, is the fact that Copernicus is user-centered. What is the meaning? Is the fact that any new satellite, any new data and information that the Copernicus core services are going to be developed must be really related on what is needed by the end users. And the end users, one of the major end users, if we consider hyperspectral mission, are really related to agriculture, and we will see why. So we are starting, you know, the third part of, you know, the Copernicus evolution, putting regulation like this one that is really evident how much a Common Agricultural Policy payment can use the Earth observation implementation. So how can you use the hyperspectral information that we can get from hyperspectral satellite. So this is really important because what we are developing, what we have developed, and we are going to still develop in the next years, is the fact that we have consolidated what we have called the requirement consolidation studies. So what are the requirements, both in terms of user need, but also, you know, technical in terms of like user requirements? How can this can be translated in some practical and operational indicators and information that can be used from the final end users that are government, regional agency, and so on. This is really important. Just to have like a very quick overview, the Copernicus evolution, so the new monitoring mission, the Copernicus 2.0, are covering several important thematic areas. We go from anthropogenic CO2 monitoring mission, the one with polarized and snow topography, passive microwave radiometer, land surface temperature mission, L-band SAR mission. But what we are going to talk about today, and that is, you know, important and of interest of the audience, is the CHIME hyperspectral imaging mission that is really focusing on food security, soil, and biodiversity. So how can we get out a lot of information that can be used for food security, soil, and biodiversity? So The key mission application has to provide routine hyperspectral missions, hyperspectral measurements in support of what I just introduced AU and related policies for the management of natural resources and assets. So it's really focusing on food security, agricultural raw materials, and soil properties. So the brief results, and you will have, session hands-on from Emiliano later on, that will show you how can we use the CHIME operational mission that will be launched at the 2028, but how can we already use and test using the PRISMA Italian mission to, let's say, deliver really useful information for that. So you can have also to consider the secondary applications, so biodiversity and ecosystem sustainability, forestry management, environmental degradation, lake coastal ecosystems. So you have a wide spectrum of thematic area that can be of interest for using hyperspectral data and information. The really important thing is that the key mission requirements that are going to be, applied to the CHIME mission is that has to be deliver a routine hyperspectral observation. So right now we have as PRISMA, a scientific mission. So we have to turn PRISMA into an operational mission. So here in the mission requirements, we have the sun synchronous orbit. You have a revisit time planned with 2 satellites is 12.5 days. We have also to consider that all the mission that are already running, and they are going to run like Nmap, SBG, but PRISMA and PRISMA second generation, can be considered also as a contributing mission to this operational hyperspectral system. So it has an area view covering land surface, inland and coastal water, and a spectrum range that goes between 400 to 2500 nanometers. So you have a spectral bandwidth of minus 10 nanometers with SST of 30 meters. So we have a high radiometric accuracy, low spectral spatial missing registration, improve needle requirements. So really important to match performance of parallel mission, so Nmap, PRISMA, and SPG. So you can consider how much the availability already of PRISMA and also the implementation of PRISMA second generation represent a valuable real data that can be used in that direction. So the research group has working since 4 years, and it will still last for another 2 years on the consolidation of algorithm using the precursor mission of PRISMA. That was, one of the major points. So you can have like a view of a database of hyperspectral sources that were used, and you see that we are already discussing with SPG, so NASA JPL, which are the SPG algorithm class and the algorithms product that we can discuss in terms of what we are developing in terms of requirement consolidation in Europe and what they are already discussing at the SPG group. The ongoing project that allowed this research group to do this huge work was, of course, as a primary funding, the CHIME requirements consolidation studies funded by ESA, but we have added in due course other good projects, and especially ASI for the PRISMA Science Overseas, where we are going to test global ECV multi-sensor mapping for coastal ecosystem services. But also, you look that we are also discussing carbon observatory, so mission science team project funded by NASA, so space-based detection and quantification of CO2 point sources. So you see that the wide range of data and information are quite extended. So the CHIME requirements consolidation study is funded by ESA, is a project ITT, and we have to focus on potential value-added correct sentinel mission in this main domain, agriculture and food security. And you see at the very beginning that why ESA was interested, because the European Commission that is funding Copernicus is really interested in how much this can be used into real policy implementation, but also related to geology and various application domains. So the project was to follow up on previous studies with the aim of extending a bibliographic review but really identifying algorithm and approach for defining, improving the high priority products. By means, in this case, we were really focusing on linear hyperspectral mixing analysis in order to obtain really good results regarding the possible improvement of what CHIME is bringing into the Copernicus mission compared to the Sentinel-2 mission that is already operational. So just to be more quick, we have thematic areas with agriculture and food security and geology and minerals. So you have a thematic area that are really linked to user requirements, with assessment of biophysical and biochemical variables related to crops and agroeconomic interest, topsoil and raw material detection. And you can see which are the variables of the candidate high priority products that we were testing and we will still keep testing. So the leaf canopy pigment content, light canopy water content, but also related soil organic carbon and soil texture and a specific mineral identification. So we have also already implemented which are the CHIME candidate algorithm, and we have seen the table that also SBG is doing. So now the connection is really discussing with ASI, SBG, and CHIME, which are the candidate algorithms that can be used. What I'm going to show you are some really short example on what we have used in subpixel linear mixing as a clear, robust candidate algorithm, because we have to consider that when we talk about operational services, it has to be applicable in several places around the world. So it has not to be, in situ data driven. So based on that, the data set that we have analyzed are based on what we have CHIME simulation data, but all the Prisma data that are already available, and we had campaigns also with Aviris acquisition in specific area. And of course, we are still using the Sentinel-2 because we have to prove to the European Commission which is the value-added product that we can get out from a hyperspectral mission in compare of Sentinel-2. So based on that, we were testing into 3 test areas in 2 different crop system. So we have 3 different areas, one in the northern east part of Italy, that is Yolanda di Savoia. We have an area in Tuscany and another area that is Biancane, that is really related to its raw material. So we have tested topsoils and vegetation in test areas 1 and 2, and raw material in the 3rd test area. So we have applied techniques that are based on the principal component analysis of the image and the pixel image based, but we have also added the in situ campaign and Aviris campaign acquisition, so airborne acquisition. So we have applied 2 different algorithms. One is the linear spectral mixing analysis, and one the multispectral mixing analysis, that is the MESMA. One is based on the n-member selection, based on image analysis. The other one is based on the ROI collection, so in a region of interest. So it's a sort of like pre-trained, and we will see which are the difference, but we will see also really good evidence on how much the hyperspectral can give in this sense. So as a first results, you can see that with hyperspectral based on Prisma data, we have used the spectral mixing analysis to extract the collection of 4 different n-members spectral signature. So we have seen that there was a redundancy. So specifically, we select 3 main n-members for running the spectral mixing analysis. And you can see that we have fractional Budnard maps with variability, especially in this test case for soil topologies for unhomogeneous pivot into a crop analysis. So if we look in the evolution and with the comparison Prisma and CHIME-like data in the site 1 of Grosseto, Italy, you can see that there's already some good evidence how much the CHIME-like sphere interval show high percentage of covariance associated to the principal component 1 in comparison with the very near interval in this near interval instead of the covariance percentage of prisma with the near and sphere intervals are quite similar. So you can see that we are already putting an evidence on how much could be the improvement. So the spectral dimensionality shown by the feature space represented by the 2 interval of prisma and CHIME light has a similar shape. This is really important because if we go into the in showing the different approach, we can have a different set of n members. So the linear shows an n member distribution mostly related to vegetation and fractal abundance, while the sphere allow for identifying the soil topologies. So this introduces one of the most important evidence when we have to prove why an hyperspectral mission is a value added. So you really start to separate, what is a vegetation signature and a topsoil. So if we go on a fractional abundant maps of prisma data based on linear spectral mixing analysis, you can see that you can have in terms of abundant maps in comparison with Sentinel-2, you can start to detect different things, and you can see that we have also extracted the fractional abundant maps both for vegetation, dark soil, but also what are the candidate high priority mission with 30-meter resolution, that is clay and sock. So the first take-home message is when compared with Sentinel, Prisma already showed that you improve capacity for distinguish topsoil variable cover distribution. This is already an evidence why we have to invest and continue to really studies the evolution for the hyperspectral mission. So hyperspectral narrowband, that is the second take-home message, data instead of multispectra allow for studying further variables and their fractional cover composition. This is really important, and I will go to the second slide with example where you have the 2 approach, the linear spectral mix and the MESMA with the region of interest based analysis, and the one with just principal component based analysis. And you have quite an evidence with the ROI based analysis. We obtained 93% more or less of classified pixel, while with the principal component analysis based analysis we obtained 98% of classified pixel. So we use both with a constraint of 2 n members for each pixel model. This is really important because, of course, ROI, so region of interest based approach, is a sort of supervised. So we sort of know in advance what could be the fractions already with a meaning, while instead the pure principal component based analysis should be interpreted. But this is really good because when you have to deliver an operational product for the, let's say, land cover, land use operational services, it's really important to have this approach. So next steps and take-home message. So it's already evident that already with Prisma, we are able for testing the value added by satellite hyperspectral data in biophysical value retrieval, specifically in agriculture and food security. And this is really important because we have a European law that is really asking for that. So it's really binding. So the principal component analysis on separate linear and sphere wavelength allow for obtaining a finer grain identification of specific end members and subsequent fractional cover maps. And fractional cover maps are the first step to obtain a land cover, land use, and thematic map. And this is really one of the major outputs that we can get out for operational service. Of course, a new generation of satellite hyperspectral sensor should consider new compliance of switch sensor. So we have seen that already seen good results for topsoil thematic areas on Prisma sensor. We have already demonstrated that the 2 algorithms, linear spectral mixing analysis and the MESMA, show higher reliability in modeling each pixel composition. So this allow, especially to the MESMA, can be exploring, allowing and building a wide arbitrary spectral labyrinth. And this is really important. Of course, there's a CHIME requirements consolidation study that will still go for other 2 years. Will bring experts to consolidate and develop. I will skip briefly that, and I will try to conclude why, I'm happy to contribute to this session, because there's a lot of collaboration opportunities. It could be programmatic, improved observation, for the implementation, for science call. When we talk about user, also the science call and science end user are important, and also which are the application and services. In this, boundary condition, I would like, and I will conclude, to bring to your attention that what we are also doing a lot is how can bridging the potential of the use of all this data, the DIAS, the infrastructure that the European Commission put in our possibility to use, and how can we build as a research group an infrastructure to have a sort of user uptake for students. So really using the infrastructure that the European Commission is giving to us, and how we can transform all this information to operational and practical hands-on training using tools and processing. So I will not go in details, but how we studies what we have called the green infrastructure, and how much the hyperspectral data can bring to the detection of the green infrastructure in riparian zone using Copernicus program and the future hyperspectral mission. This is really important because this approach is based on indicators defined by the European Environmental Agency that is delivering the Copernicus land monitoring services, and how much these indicators can be assessed through the remote sensing techniques. So this is one of the main goals that we have with the Prisma Scienza funding from ASI, for how we can use Prisma data for, ECM multi-sensor mapping, specifically for coastal ecosystem, and how much this can be, also extended in collaboration, maybe under SIOS and so on.